Well, welcome to this video. This is Craig Hain, and this is going to be the Chapter 6 video of the book How and Why Homeschool Math Can Be Vastly Superior to Public School Math. As I said, I'm Craig Hain, and I am the CEO of Triad Math Inc., which is a publisher of this book and the creator of the program I'm going to be telling you about. Now, this is Chapter 6 of the book, and this is going to be the longest and most challenging chapter for a homeschool parent. But if you have a child that might be interested in some STEM subject, like science or engineering, then this is definitely a chapter you need to try to understand. It'll be very challenging, particularly if you don't know a lot of math. Although I think you'll get the right idea, and I think you'll understand it. I'm trying to present this to somebody. It'll be more meaningful if you know math, but I think it'll be meaningful no matter what. Now, as a matter of fact, if you know somebody that's a STEM person, you might want to have them read this chapter or watch the book. This is a long chapter. It's 8 pages long, and the video is probably going to be an hour or so. I don't know. It's going to be quite a video. Now, this chapter is going to explain, in essence, why homeschool math today can be vastly superior to public school math. And it's just plain superior because of spike pedagogy and other things, but when it comes to STEM, it's a huge difference. Now, there's two approaches to learning math. There's what I call a heuristic approach and a rigorous approach. Now, a heuristic approach is really an approach where you learn math learn how to solve problems and understand things by using a practical method that's very intuitively obvious and makes sense. It might not prove anything and be optimal, but it's really a great way to learn math, particularly in the beginning. That's what our ancestors used for thousands of years. Now, a rigorous approach is where you're trying to prove something logically from a well-defined set of assumptions called axioms, or you're proving a sequence of lemmas of theorems, and you're using logic, and everything has got to be rigorous. And this is what mathematicians do now, and they've been really doing this now very vehemently since the mid-1800s. And so I would say that it turns out that modern mathematicians and some of the math educators today always try to use a rigorous approach when they're teaching math, but it can be very tedious, very boring, and quite difficult to understand. And quite frankly, I believe the heuristic approach is much better. That's what our classical mathematicians used really throughout history. And now Euclid did use a more rigorous approach. But Archimedes and many other great mathematicians all the way through the 17th century and the 18th century used heuristic math. Now, there's a wonderful 20th century teacher named Dr. George Simmons you'll learn more about. He wrote a wonderful book that I use in my program called Pre-Calculus Mathematics in a Nutshell. In fact, it's the only textbook I use in this whole 6-tier program. And I believe that any parent or teacher ought to read George's preface and the 3 introductions to the 3 chapters, geometry, algebra, and trigonometry. If you just read those introductions and the preface, that'll teach you a lot about the philosophy of teaching math. You can go to Amazon and get the book. It's about $15. In fact, I say, hey, I wonder why it isn't adopted by more high schools. Obviously, it hasn't been promoted because it's very inexpensive. And I will tell you that I consider that Dr. Simmons is the great math teacher of the 20th century. He wrote what I consider the very best calculus book and differential equations book before he wrote this pre-calculus book. He's a great teacher. And as a matter of fact, before he even wrote those books, he wrote a book on topology and modern analysis. Now, this is the most advanced math normally taught in undergraduate school and first-year graduate school. It's the basis of all modern theoretical subjects like theoretical physics and quantum theory. And I used this book when I taught as a professor in an engineering school at Indiana State University. I began to use this book. That's how I met and became acquainted with Dr. George Simmons. And then later on, I used his calculus and differential equations books really to learn better myself. And then finally, the pre-calculus book came out in 1988. It was just phenomenal. Now, the question is, what should we be teaching our high school STEM students that's going to get them optimally prepared for a great university STEM education and also prepare them to compete with the best trained students in the world, the international students and the best trained students in the world? What should we be teaching our high school students? Okay, Well, the first thing is numbers. They have to learn about what are called real numbers. They need to learn what are called hyperreal numbers, which is not taught today at all in even our schools and colleges, and complex numbers. Now, we need to teach these number systems heuristically, not rigorously, not in the beginning, heuristically. And it can be done. They'll understand them quite well. That doesn't mean we don't use good arguments, but we're not rigorous. We're not pedantic. Well, real numbers, you may know already, are numbers that correspond to all the points on a straight line, and they can be expressed with our decimal number system in terms of, how you can take any kind of a number and express it as a decimal number. Now, subsets of the real numbers that we start with are the natural numbers, the counting numbers, then the negative integers, the negative numbers, integers, rational numbers, which are fractions. And all of these are numbers that a STEM student has to understand heuristically. And that's, of course, what we teach in our program. Now, I will tell you this, non-repeating decimal numbers, if they exist theoretically, are called irrational. And there's two subsets of them. There's an algebraic irrational and transcendental irrational, which doesn't matter. But these are only of interest to theoretical mathematicians. You'll never run across an irrational number when you're doing science or engineering, because you're always going to use truncated decimals, which are rational numbers. Now there's a number called complex numbers. And these are numbers that correspond to points in a two-dimensional plane. Really not very hard to understand if it's taught heuristically and properly. And I will tell you it involves trigonometry functions and infinite series, and complex numbers are vital for many STEM subjects. So of course, naturally, I teach that in Tier 4. Now there's something called hyperreal numbers. And these are the real numbers that everybody knows about, and they also include what are called infinitesimal numbers. Probably never heard of that, did you? Well, let me tell you this. Our ancestors approached numbers heuristically into the middle of the 19th century, the mid-1800s. And then they began to approach numbers rigorously, and they had to use axiomatic methods and prove everything rigorously. And it's much more difficult to numbers than the heuristic approach. And it's probably not what you should teach a student until they decide they want to be a theoretical mathematician. But here's what happened. In the 1800s, there was a great split between applied mathematicians and scientists and theoretical mathematicians, because in the 1800s, they couldn't figure out how to include infinitesimals in a rigorous treatment. And so what they did is they banned them. Now, ironically, in 1966, they finally managed to get infinitesimals back into a rigorous treatment. That was done by, I'll tell you just in a minute, Abraham Robinson. So let me tell you this. Mathematicians, from the very best ancient Greek mathematician, who was Archimedes, used infinitesimal numbers. And Archimedes used infinitesimal numbers, for example, to prove that the area of a circle was related to the ratio of its circumference and its diameters, what today you would call pi r squared. But Euclid hadn't done this in his rigorous approach he wasn't able to do this with his rigorous approach to geometry. Archimedes did it with a heuristic approach using infinitesimals. And he did much more than that. In fact, you want to see Archimedes' tombstone in my Tier 2. That's a really fascinating story, and it involves spheres and cylinders. Now, the creators of calculus back in the 1600s, Leibniz and Euler was in the 1700s, they utilized infinitesimals all the time. And when they created calculus and then differential equations, they used infinitesimals. And so applied mathematicians and scientists and engineers have always used them extensively. But when the theoretical mathematicians began to make these number systems rigorous in the mid-1800s, like I said earlier, they couldn't figure out how to include infinitesimals. So what did they do? They banned them. They said, infinitesimals aren't actual numbers, and they banned. Now, I will tell you this. All numbers are theoretical. All numbers are theoretical. They're really a concept, and then we use them then to build models. I don't want to get too much into that because it gets pretty esoteric. But applied mathematicians and scientists just went on using them because they were so valuable heuristically, infinitesimals I'm talking about. But unfortunately, theoretical mathematicians influenced the writing of our calculus books for the 20th century. And they went a rigorous and a difficult way. They did not use infinitesimals. I consider that was a horrible setback for math education. They rationalized it by saying, well, if you can't do it rigorously, it's not valid. Well, that's nonsense, of course, but that's what they believe. Well, then in 1966, Abraham Robinson figured out a way to make infinitesimals and hyperreal numbers, and they're called rigorous. So they're back in since 1966. That happened to be the year that I got my PhD, just coincidentally. Now, unfortunately, our calculus books, even today, haven't caught up yet. Wonder why? Well, I don't know. Could it be they got a huge investment in the old-fashioned calculus books that use the epsilon delta rigorous approach? I don't know. Now, I use the infinitesimals extensively when I teach calculus in Tier 5, and I start using them in Tier 4 because it's a very, very good heuristic way of teaching. So that's, first of all, a very important thing. It's not nearly the most important thing, but it's certainly an important ingredient in the pedagogy and the content of how I teach it. That's not what makes it vastly superior, though. That's another reason for that. You're going to find out in a little bit. Well, first of all, now you may not understand this if you don't know mathematics, so just kind of listen to it and you'll recognize some of the words. What are the ingredients of STEM math? What do you got to teach a student in STEM math? Well, you got to teach them algebra and geometry and analytical geometry and trigonometry and calculus and differential equations. All of these things are absolutely required if you're going to study science and engineering. Now, the basic concept that's used throughout this is called functions. And there's different kinds of functions. There's polynomial functions, trigonometry functions, exponential functions, and their inverses. Then you have something called infinite series, and these are like infinite polynomials. Now, if you don't know what this means, don't worry about it. It's just jargon. If you know math, you'll know what I'm talking about. Then, of course, you have to have tools to analyze the functions and to solve the STEM problems that involve functions. You have to have tools to do this. Well, one thing you've got to do, you've got to graph a function, get a visual picture of it. And this used to be done manually. It's very tedious to do. You had to calculate the values of a function, lots of points, and connect them. Then they came out with graphing calculators, which was nice and dandy, but there's a much better tool today I'm going to tell you about. Well, then, of course, calculus. Now, calculus, it actually involves two different tools that analyze the behavior of functions. And it helps you understand their visual representation, which are called graphs. It also helps you figure out what is the area under the graphs. Very important concept used throughout STEM, throughout science and engineering. It's called differential and integral calculus, the two different tools, so to speak. And then there's something called the fundamental theorem of calculus, which connects these two. And it's the most important math theorem probably ever was. It was discovered by both Isaac Newton and Gottfried Leibniz independently in the 1600s. And it's the reason we're here today. This is the theorem that underlies modern technology and modern science. Without the fundamental theorem of calculus, we wouldn't have gone forward. That was really the key to get the modern scientific revolution started, which led to modern technology and the modern civilization we live in. Fundamental theorem of calculus. Now, I actually have some free videos. If you go to the Homeschooler Today, the free resources, I've got some videos that explain the concepts of these and the fundamental theorem. The concepts are easy to understand. Okay, then came what are called differential equations. Now, a differential equation is like an algebraic equation, except the solution is a function. And this is what's used throughout science and engineering. Differential equations are how you set up physical models, and then you have to solve them to find the function for that model. And it's this used throughout, so it's critical. And it's an extension of calculus, actually. Now, I realize that most people that are reading this chapter or watching this video are probably having difficulty understanding what all this means. If you don't have a math background, you don't really understand it. And for what it's worth, I'll tell you, a lot of current high school teachers don't understand a lot of this either because they haven't been taught it. But this is what a student's got to learn if you're going to master a STEM subject, and particularly if you want to compete with other well-trained STEM students. The international students that we get today, many of them have been trained properly, which is what we're talking about. Math is the foundation of all STEM subjects. You simply have to understand STEM math. And it's based on functions, which are used to build STEM models, and then you have to use those to solve problems and understand all these STEM topics. Now, any homeschool parent that has a STEM student, someone that might be interested in science and engineering, got to deal with this. In fact, any parent, whether they're homeschool or not, is going to deal with it. So this is how you're going to do it. So now I've got to tell you about, here's the fundamental problem with what I call the standard math curriculum, which is what's being taught in virtually all of our high schools today. And here's the problem. Wonderful manual tools were developed to deal with all these topics I mentioned above by our ancestors. And they basically only had pencil and paper or something equivalent to it. So they had to develop all these manual tools and algorithms to solve calculus and differential equation problems and deal with trigonometry and all of that. Now, these manual tools that they develop are difficult to learn. They're difficult to master, and they're difficult to use. In fact, this is the main reason so many students develop an intense fear and dislike of math. And I don't blame the students. It's really a problem. It's a great struggle for them. You've got to deal with numbers and arithmetic calculations. And of course, they developed algorithms for doing this: addition, multiplication, division, square roots. You learned this in school, probably. There's all kinds of manual pencil and paper algorithms to do it. And then you have complex numbers, and they had algorithms for that. Now, logarithms, by the way, which are that's a function, inverse of the exponential function, became a wonderful tool for performing arithmetic a few centuries ago. And the slide rule, or what we call the slipstick, became a wonderful tool, used logarithms. And it was used by all scientists and all engineers for centuries to do arithmetic problems. In fact, it was a great step forward in order to be able to do the calculations you needed to do. And then they developed what are called tables, trigonometry tables, and logarithm tables were created. And these were an indispensable thing in solving math problems. And then, of course, as I said, calculus was developed in the 1600s and was the foundation of modern science and technology. Newtonian physics started, Isaac Newton started it. And calculus now is used to analyze functions and to create them. You got to use calculus. You use differential equation to create functions. Now, the manual tools to do this were developed by Leibniz in the late 1600s, and one of his greatest disciples was Leonhard Euler in the 1700s. And they developed wonderful, wonderful tools to do this, manual tools. And then, of course, as I said, we had to learn differential equations, which often led to what are called special functions. The ordinary functions I mentioned above are not adequate. You need a lot more functions. They call them special functions. And by the way, they don't even teach this today in calculus. It's too difficult. Now, all these manual tools were very, very difficult to master and difficult to use. So if you wanted to become a STEM professional, you had to learn these manual concepts and tools. We had to learn the concepts were easy, but the tools were hard. Now, you had to be intelligent, but more important, you had to be very dedicated. You had to work very hard. And lots of very, very intelligent people just said, hey, this is too much. I give up. I'm not going to do it. Math was tough. Math was considered an insurmountable barrier, or a very high barrier for many STEM students and subjects. And as you're going to learn soon, that has all changed. Now, integral calculus used to flunk out more kids in engineering school than anything else, calculus 2. And the reason is it had a lot of manual tools that were really hard to master quickly, and they used it sort of as a filter tool. If you could get through integral calculus, then you probably were going to be a pretty good engineering or science student. But then a miracle happened in 1972. I call it miracle number 1. I'm going to tell you about today. There's a number 2 coming, as you can imagine. The first scientific calculator was revealed to the world. The HP 35, Hewlett-Packard with 35 keys, HP 35. About $2,400 in today's dollars in 1972. It's $395 then. But log tables and trig tables were obsolete. The slide rule was obsolete. And now a STEM professional could do all of the arithmetic calculations very quick and very easy. And a scientific calculator not only was an order of magnitude easier to use, it was easier to learn and to solve math problems. It just revolutionized things. Now, needless to say, this was a crisis for math educators. I know, I was very tied up with this. I was a professor at the time this happened. Many of their books and their courses were obsolete. The students rejoiced. They loved the calculator. The math teachers, at least at first, hated it. It made their stuff obsolete. Many teachers were depressed. I'm talking professors now mostly. This was mostly at the university level. A lot of that was too hard to be taught in high school. Much of what they've been teaching and been earning a good living for all their lives was now in the dustbin of history. They had to adopt this new technology and this new reality. And their textbooks were obsolete. It was just an absolute disaster for the math education community. But Well, calculus and differential equations weren't affected very much. They're the workhorses of STEM, I've told you already above. And they weren't affected very much. You still had to develop all the old manual techniques, because that's all we had. The things developed by Leibniz and Euler in the 1700s and the 1800s. And so advanced STEM math didn't change very much at that point in time. But 2009, a massive educational STEM math earthquake, even more significant than the 1972 miracle that I just told you about. Now, in order to understand this earthquake, unfortunately or fortunately, I need to give you some background of how it came about. First of all, you probably know that computers were developed shortly after World War II. And they really took off in the 1950s, and then first it was vacuum tubes, and then came transistors, and then integrated circuits, and they got more and more powerful. And finally, in the 1970s, a sophisticated computer algebra program called Maxima was developed at MIT, and it could solve a lot of math problems numerically. It could replace some of these manual tools. It made it easier. So there was a teenager in England, the UK, named Stephen Wolfram. And somehow he got access to Maxima at MIT. I don't know how that happened, but he did. And he started solving physics problems as a teenager and publishing them. And they were so impressed, people thought he was a genius, although he admitted that it was because of this tool that he could do it. And so then he ended up going to the greatest physics graduate school in the world, Caltech. Richard Feynman, the great, brilliant quantum physicist, was there. And so was Murray Gell-Mann, the guy that invented the Standard Model. Anyway, Caltech, the great physics school. And guess what? He earned his PhD in theoretical physics at age 20 in 1978. Why? Because he had the tool. He could do things that you couldn't do manually. And he was given a MacArthur Genius Award, lots of money. Well, Wolfram wanted to develop a much more powerful tool than Maxima. He loved Maxima. He said, hey, we could do a lot better than that. And he went to work on it, and over a 10-year period, it's a long, involved story I won't get into. It's a wonderful story. He was able to do so. And in 1988, he introduced something called Mathematica to the world. Now, Mathematica is an incredible programming language, unlike anything that came before it. It was just like, people that use it, it was like truly a miracle at that time. But it was hard to use. It was expensive. Now, Steve Jobs incorporated Mathematica into the next computer. The 1988, remember, he left Apple in 85, and he put it in the next computer. And this is the system that was used by Tim Berners-Lee at CERN in Switzerland to create the World Wide Web. That's how powerful it was. I don't guess we'd have a World Wide Web if it hadn't been for this, or it had been done differently. Now, here's the thing, and this is now what I'm going to tell you. Miracle number 2. Stephen Wolfram introduced an absolutely incredible tool to the world in 2009 called Wolfram Alpha. There's the website. Go to the website and look at it. And guess what? It's hard to believe. Wolfram Alpha will solve any calculus or differential equation problem immediately. And that includes problems you can't even solve with classical techniques. And it does much, much more than that, but it does that. So Wolfram Alpha is more revolutionary for STEM math than even the scientific calculator, if that's possible. It's just unbelievable. It revolutionizes it completely. Okay, we can start now as early as middle school and begin to teach math to students that's virtually impossible to teach with the old and obsolete manual tools. We're in the 21st century now. And we can utilize this amazingly modern tool to teach all STEM math. And we do it in our program starting back in Tier 4 with algebra and geometry. We begin with conic sections. Then we go on into Tier 5, and I'll show you the syllabus in a minute. And we do calculus. And then we have Tier 6 for differential equations. And a student can learn all this in high school. You can't do that today in a public school. Public schools don't even teach differential equations. They don't even really teach calculus very well, usually. And now you can do all that. You can learn the concepts of calculus are easy. It's the old manual tools that are hard. And Wolfram Alpha changes all that. You can learn calculus now, good enough for MIT in one semester. Ditto for differential equations. Concepts easy. Manual tools hard. Wolfram Alpha easy. So a student now can learn all the STEM math you're going to need for science and engineering in a small fraction of the time and effort that it used to take. A small fraction. In fact, the math barrier is gone now. Wolfram Alpha is like drilling a huge hole through the math barrier. Now, unfortunately, all high school books are obsolete. And that's true of calculus books and differential equation books too. They're obsolete too. Why is this? Well, they're loaded with all the old, obsolete manual tools that are very difficult to master and use, and no one uses them anymore. No modern STEM professional is going to use these old manual tools. It's crazy. It's like, would you do your arithmetic with pencil and paper when you got a calculator? Well, you're not going to do calculus and differential equations, solve the problems in the model with the old manual tools. You're going to use the new tool. Now, there are some other tools, by the way, besides Wolfram Alpha that came along, but they're expensive and hard to use. Wolfram Alpha is free, and it's easy to use. Now, you don't need a book today to learn calculus and differential equations. All you need is a few notes, some exercises, some videos that I've created, and Wolfram Alpha. And, of course, we deliver it with Spike pedagogy, which you learned about in chapter, I think it was chapter 1, most important pedagogy. Now, unfortunately, the math educators today, what I call the math education cabal, maybe I shouldn't call it that, community, whatever you want to call it, the math educators, they don't want to give up a multi-billion-dollar set of products. I mean, look at I tell you, all these books are obsolete. It took them decades to develop it. They've got huge investments in it, and they make billions of dollars selling them. I can't blame them from a business viewpoint. I don't blame them any more than I blame the engineering professors that didn't want to abandon slide rules and log and trig tables in 1972. But that's the world we live in. Think of smartphones today. They replace landlines and many other classical obsolete technologies now. Look what you can do with a smartphone. Look at everything you can do with a smartphone, and look what it replaces. If you go back and analyze it, a smartphone today, which you can buy for $80 and $40 or $50 a month, use it, would have cost you, well, it just does things you couldn't even do back then. And by the way, I mentioned Wolfram Alpha. You've heard of Siri on the iPhone, right? Siri is based on Wolfram Alpha. Did you know that? In fact, there wouldn't be an iPhone today if it wasn't for Mathematica. Steve Jobs and Steve Wolfram worked together, and there's all kinds of algorithms in the iPhone based on Mathematica. And Siri being the obvious one is based on Wolfram Alpha. Well, the standard math curriculum today, quite frankly, is like teaching carpentry with the old manual tools of the 17 and 1800s. Go visit a museum sometime and look at the tools that the carpenters used in the 17 and 1800s. And just imagine how difficult it was. In fact, you won't know what most of them did. You wouldn't even know how to use those tools. They're hard to use. Now compare those tools to modern electrical tools. Let's take an analogy. There's a concept, a hole in a piece of wood. That's a concept. Almost anybody can understand it. How hard is it to understand what is a hole? Just look at a couple of holes, and you see what it is. It's an extensive definition. I don't have to define it with words. I can just show it to you. But here's a problem. How do you create a hole in a piece of wood? Let's say you got a 2x6. You want to create a hole in it. How do you create it? Suppose you don't have a tool, any tool at all. Well, I wouldn't know how to do it without a tool. Well, what was the first tool they used, our ancestors used? Well, they used a nail and a hammer. And you could drive a hole with a nail and a hammer. It's not easy to do, and you're probably going to split the wood, but you can do it that way. Well, then a manual tool was invented, a wonderful manual tool called a brace and bit. You probably never heard of it, but you can look it up. That's how I learned to create a hole when I was a boy, because that's the tool we used. It was a manual tool called a brace and a bit, and I took a lot of effort to learn and a lot of practice to master. In fact, I never really mastered it. It was too hard. It took a lot of slow effort, physical. And sometimes you couldn't drill a hole you wanted to because you couldn't get the brace and bit into it. But it was a wonderful tool, much better than a hammer and nail. So that's what our ancestors used in carpentry for years and years and years. They used a brace and a bit. But then came the electric drill. Oh my golly, how much easier it is to learn and to use an electric drill. It's much faster, less physical effort, very easy. And you can drill places you couldn't drill before. Wow. Brace and bit, obsolete, gone. Then came the electric drill with a battery. Now it's even easier to use. It's portable, more portable. You get to more places with it. You don't have to drag a electric cord around. Well, let me tell you something. Analyzing a function with the algebraic and manual graphing techniques that we often have students do is like making a hole with a hammer and a nail. Well, then analyzing a function with the manual techniques of calculus, it's better than using algebra. It's like a brace and bit. The manual techniques are very hard, very difficult, but better than a hammer and a nail. But now analyzing a function with Wolfram Alpha is like a battery-powered electric drill. Easy peasy, easy to use. So now any student can learn STEM math and apply it very quickly and very easily. Manual calculus and manual differential equation techniques are obsolete. I'm so sorry to tell you that all the calculus books that are in existence today that I'm aware of, and differential equation books, even including Simmons, are basically obsolete because they are so full of the manual techniques. The concepts are easy. I still recommend Simmons books if you want to learn concepts, but I wouldn't advise you to try to learn the manual techniques. Math is no longer a barrier to learning STEM math. Wolfram Alpha is like a big hole through the barrier. And that, my friends, is why homeschool math can be vastly superior to public school math. Now, eventually public school math is going to catch up, I hope. But it's a multi-billion-dollar industry that's going to have to transform. Math teachers are going to become more like coaches because you have to use spike pedagogy to deliver it. You can't do that in a classroom in a group setting. So they're going to be more like coaches. And that'll be great, by the way. I would much rather teach a student math, letting him use my videos to learn all the concepts and everything, and then I can coach him. We can do projects together. We can talk about it. Oh, it's being a coach is wonderful. And if you know math, that's even more wonderful being a coach. Now, the financial results of all this are going to be truly amazing. As a matter of fact, just think of the financial results of smartphones today compared to the old technology. Just think what it was like using landline phones and long-distance calls. And do you know an 800 number back in the early 80s when I started Hain Training? An 800 number was called a Watts line. And it was $1,500 a month for 5 states. Think of that today. They're free today. Okay. Now, here's what I have you do. Go to homeschoolertoday.com and look at the curriculum, particularly tiers 4 and 5 in the table of contents. That's where we begin to use Wolfram Alpha and tier 4. Then in tier 5, we teach the calculus in one semester. And then in tier 6 on differential equations, we have it available. Now, I will also have to tell you, the news is so good. A wonderful new tool was invented in 2016. It was called the supercomputer. It's based on something called the Raspberry Pi, and it includes all the Wolfram tools, Mathematica, Wolfram Alpha, and a brand new thing introduced in 2006 called Wolfram Language. It's a new programming language that is unlike any programming language in the world. It's wonderful, and it's included in the supercomputer. So I highly advise you, when you're able to get one. And by the way, the supercomputer is not very expensive. It hooks to any kind of a TV, through a cable, any kind of a keyboard, and so on. Okay, so what should you do? Well, in my view, you should just get started. Just get started. Enroll your student into our program and get started. Now, you're going to start with tier 1 and tier 2. We're going to climb the ladder, but if the student knows a lot of math already, that'll go real fast. You're going to get them up into tier 4 as quick as you can. And I'll guarantee you there's a lot of stuff in tier 4 they don't know. I'll guarantee you that. I don't care how much math they studied in high school. There's all kinds of things in tier 4 they don't know. In fact, I'm going to do an addendum video to this because this is already gone so long. And I'm going to talk to you specifically about the content of tier 4, 5, and 6 on the addendum video. Probably the family plan is your best way to do it. Go check out the curriculum and the pricing at Homeschooler Today. And remember, you can get started risk-free. Try it for a month and try it. If you don't like it, you cancel it, get your money back, no money. It's very inexpensive to use compared to any other program I'm aware of. You're going to basically get me as a tutor for less than $1 a day via the videos, the online videos, and the exercises, and the learning management system. And remember this, as I've told you before, you are the coach, and I'm the teacher. We have to work together. Together we can give your STEM students a great math education, far superior to any high school I'm aware of today. And if you know of one, let me know. I would love to know. And just remember this, whenever you teach math, you need spike pedagogy and proper content, which is what we deliver. And you're the coach, and I'm the teacher. And this is Dr. Dale. And if you want to see the details on the actual curriculum for Tier 4, 5, 6, watch the addendum video to Chapter 5. And I wish you the best with your STEM student and your life and your student's life. And that's what we're all in it for, right? To make students' life better. Dr. Dale, see you on another video.